If you reach out right now and just rest your hand on the desk in front of you, or maybe grip the steering wheel if you're driving, just take a second to really feel it.
Right, it feels completely solid.
Exactly. It feels totally inert, doesn't it? It's room temperature, it's solid, it's calm. To our human senses, it is a perfectly stable, quiet arrangement of matter.
And that is arguably the ultimate illusion of the macroscopic world.
Yeah.
We have evolved to be entirely comforted by that stability because, well, if our senses could perceive what was actually happening at the subatomic level, we would probably be in a constant state of sheer panic.
I think you're putting that mildly.
Yeah.
Because what if I told you that inside every single proton of that desk, inside every single atom of your own hand pressing against it, there is a trapped inferno burning at an equivalent of 458 trillion degrees?
Which is, yeah, it's a number so staggeringly large that it essentially loses all meaning in everyday physics.
Completely loses meaning, yeah.
Just to put that in perspective, we are talking about internal energy densities that perfectly match the electroweak epoch of the Big Bang.
Right.
We are talking about the exact kind of heat that existed fractions of a second after the universe was born. And it's just sitting there, hidden in plain sight, completely localized inside every single particle of your body.
It is wild. And with that, welcome back to the second installment of our special deep dive into the Redefined Mass framework. We're continuing our journey through a really fascinating stack of sources today.
Specifically, we're looking at the groundbreaking theoretical physics papers published by Vrbovsky-Banić and Pavel Vrbovsky.
Right, alongside some of their supplementary notes on solar anomalies. Our mission today is to tackle three massive, just universe-breaking paradigm shifts that their framework introduces.
And we really have a lot of ground to cover today.
We do. We have a ton to get through. We're going to start by exploring the entropy paradox of the vacuum, which is exactly what we just hinted at with that crazy 458 trillion degree temperature.
Yeah, the hottest freeze in the universe, as they call it.
Exactly. Then we are going to take that brand new understanding of what matter is, and we're going to throw it into the ultimate cosmic pressure cooker to solve a decades-old mystery in solar astrophysics known as coronal heating.
That's postulate X6, which is just brilliant.
It really is. And finally, we are going to look at the true physical origin of the universe's most mysterious number, the fine structure constant.
It's such an incredible narrative arc when you lay it out like that. We are moving from the unimaginably small and paradoxically freezing cold interior of a single particle, scaling all the way up to the explosive surface of the sun, and then
finally diving into the structural geometric blueprints of reality itself.
right, the math that holds it all together.
And as always, for you listening, you do not need a PhD in quantum field theory to follow along with us. We're going to unpack this step by step. We're leaving the heavy, impenetrable jargon at the door. And, whenever we hit a complex concept, we're going to break it down.
We really want you to get those genuine aha moments about how the universe fundamentally fits together.
So let's jump right into this entropy paradox. Because I have to admit, I am completely hung up on this number. 458 trillion degrees.
It's hard to swallow.
My brain just immediately rejects that. How on earth do Banić and Vrbovsky even arrive at that figure?
Well, to understand the math, we first have to completely dismantle how standard physics teaches us about mass. We have to look at how this specific framework redefines a fundamental particle.
Okay, so a total teardown of the basics.
Basically, yeah. In standard models, mass is often treated as a bit of an abstract property. It's just, a number assigned to a point. A particle just has mass the way an object has color.
Right, it's just an inherent trait.
Exactly.
Yeah.
But in the Banić and Vrbovsky framework, the unperturbed rest mass of a particle is a literal physical structure. They model it as a localized spherical bubble of virtual bosons.
Virtual bosons.
Specifically, a highly dense gas of virtual photons.
Okay, let me stop you right there to make sure we're on the same page. When you say virtual photons, I instantly imagine a trapped cloud of light. But why use the word virtual? Are they different from the photons coming out of the lamp on my desk?
That is a crucial distinction to make. Real photons, like the ones from your lamp, travel freely through space. They carry energy that you can see or feel as heat on your skin.
Right, they move from point A to point B.
Virtual photons, on the other hand, are transient fluctuations of the underlying electromagnetic field. They are constantly popping in and out of existence, exchanging forces, but they don't travel vast distances like light.
So they're more like local vibrations.
Exactly. In this framework, a fundamental particle is essentially a stable, localized boundary that traps a highly concentrated gas of these virtual photons.
Okay, so it's a tiny structural cage holding onto a storm of fluctuating energy.
Precisely. And because it is a trapped gas made of spin 1 bosons, which obey specific quantum statistical rules, you can actually apply established thermodynamic principles to it.
You can treat it like a regular gas.
Yes. So Banić takes this virtual mass shell, this trapped gas, and he applies an isomorphism of the Stefan-Boltzmann law to it.
The Stefan-Boltzmann law. Okay, I remember hearing that in high school physics, usually in relation to stars or glowing metal. That's the one that relates the temperature of a black body to the energy it radiates.
So
Right?
you're touching on the exact right idea, yes. But let's reframe that for the quantum scale. In classical physics, a black body is an idealized object that perfectly absorbs and emits all frequencies of radiation.
Right.
The Stefan-Boltzmann law basically states that the total energy radiated by this body is proportional to the fourth power of its temperature. It's a way to link the raw energy of a system directly to its thermodynamic temperature.
So Banić takes the mathematical architecture of that law and just maps it onto this trapped gas of virtual photons.
He does.
So he's treating the inside of a proton like a microscopic oven.
That is actually a really brilliant way to visualize it. By integrating the energy of all the occupied quantum modes across this virtual frequency spectrum inside the quote-unquote oven, Banić derives a thermodynamic mass equation.
Okay, tracking.
He is basically calculating the total latent heat of this trapped quantum gas. And then he equates this new thermodynamic expression to Vrbovsky's previously established classical virtual mass expression for a rest state proton.
And when you smash those two equations together?
That is exactly where the math gets breathtaking. You isolate the thermal energy packet in that combined equation and you just solve for temperature.
And out pops the massive number.
Right. The result is an equivalent vacuum temperature, which the papers denote as T subvac of roughly 39.5 GeV or giga electron volts.
Now, in particle physics, I know scientists use electron volts to describe energy and mass interchangeably, right? Because of Einstein's E equals mc squared.
Exactly. Mass and energy are equivalent.
But for those of us who don't think in giga-electron volts on a daily basis, what does 39.5 GeV actually translate to in a standard temperature scale?
Well, when you run the conversion from energy to Kelvin, that 39.5 GeV translates directly to 4.58 times 10 to the 14th Kelvin.
458 trillion degrees.
Yes.
Okay, I have to push back here.
Yeah.
Because mathematically, I can see how you plug numbers into an equation and pop out a giant figure.
Sure, the math is just math until you interpret it.
Right, but physically, here's where it gets incredibly counterintuitive. It's like finding out that the plastic thermos on your desk is currently holding a perfectly preserved, microscopic piece of the Big Bang.
That's a great analogy.
But the thermos itself is cool to the touch. If every single atom in my hand is made of protons that are internally burning at trillions of degrees, why is my hand instantly incinerated? Why doesn't the Earth just vaporize?
And that right there is the crux of the entropy paradox. And the way Banić and Vrbovsky resolve it is honestly one of the most beautiful pieces of physics in their entire framework.
I need to hear this, because right now it sounds impossible.
The key here is distinguishing between two very different concepts that we usually lump together in everyday life. We have to separate latent energy density from thermodynamic entropy.
Okay, we need to break that down completely. Let's start with latent energy density.
Right. The 39.5 GeV figure represents latent energy density. I want you to think of it as structural potential energy. It is the immense electroweak scale energy that is fundamentally required to physically construct and stabilize that subquantum boundary in the first place.
So it's the energy of the structure itself.
Exactly. You can't just build a proton out of nothing. It requires a massive amount of concentrated energy to form the actual walls of that localized bubble.
But where's that energy coming from?
The energy scale of this boundary is supplied by the surrounding Higgs vacuum expectation value.
Wait, hold on. The Higgs vacuum expectation value. We promised no jargon without an explanation. What is a vacuum expectation value, and what does it have to do with the Higgs field?
Okay, fair enough. Let's use an analogy. Imagine the universe is a massive, infinitely deep ocean.
Okay, an ocean.
We are fish swimming in this ocean, and we don't even notice the water around us. That water is the Higgs field. A vacuum expectation value, or VEV, is essentially the baseline pressure of that water.
So even when there are no waves, there's still water pressure.
Exactly. Even in totally empty space, the Higgs field isn't zero. It has a baseline resting energy value of about 246 GeV.
So empty space isn't empty at all. It has this constant, massive background pressure pushing on everything.
Precisely. Now, the Higgs vacuum acts like the ultimate pressure cooker walls. It provides the immense external pressure required to stabilize this trapped gas of virtual photons into a flat 3D spherical bubble.
I see.
So that 39.5 GeV is the internal latent energy required to push back against that Higgs ocean and maintain the bubble's shape.
Okay, I'm tracking with you now. The energy is there, it's real, but it's contained, it's structural. It's the pressure keeping the submarine from crushing, essentially.
Yes, that's exactly it.
But even so, I mean, heat is heat. If I have a sealed oven burning at 1 trillion degrees, eventually the outside of the oven's going to get hot. Why doesn't this internal energy leak out as heat?
And this is where the magic trick happens. And it brings us to the second concept: thermodynamic entropy. Because these virtual photons are trapped within such a tight microscopic radius, their local spatial density crosses a critical threshold.
Meaning there are just too many of them packed into too small a space.
Yes, exactly. You have a massive population of bosons crowded into a tiny volume. In quantum statistics, when that happens, they are forced to undergo a phase transition.
A phase transition, like water turning to ice.
Similar concept, but much more extreme. They actually lose their individual identities. They collapse en masse into their lowest possible collective energy state.
Oh, they form a Bose-Einstein condensate.
Yeah.
A BEC.
That is exactly right. They form a single, coherent, macroscopic quantum state.
I've heard of BECs in the context of extreme laboratory experiments, like where scientists take lasers and magnets and they freeze a cloud of rubidium atoms down to just a fraction of a degree above absolute zero.
Right. The coldest stuff in the universe.
And suddenly all the atoms stop acting like individual bouncy balls and start acting like one giant smeared out superatom.
That's a perfect visual for it. Now, in a lab, we achieve a BEC by lowering the temperature to remove kinetic energy. But inside a particle, the vacuum achieves a BEC, not by lowering the temperature, but by increasing the density to such an extreme that the quantum wave functions of the virtual photons completely overlap.
Okay, so it's pressure-induced, not cold-induced.
Right. And this is where the paradox resolves itself mathematically. When the virtual photons inside the particle collapse into this BEC ground state, the macroscopic thermodynamic entropy of that system drops to exactly zero. S equals zero.
Zero entropy. Let me make sure I'm really grasping the gravity of this. Even though the latent energy, the structural pressure inside the bubble, is equivalent to hundreds of trillions of degrees, the disorder, the chaos, the entropy is zero.
And that lack of disorder changes absolutely everything. Because it has zero entropy, it also has exactly zero viscosity. The interior of the particle becomes a perfect superfluid.
Wow. Okay, so how does that stop the heat?
Well, think about how heat transfers in the macroscopic world. If you touch a hot stove, the wildly vibrating atoms in the metal crash into the atoms of your skin, transferring their kinetic energy.
Right, heat transfer is just microscopic billiards, things smashing into other things and spreading the chaos.
Exactly. In thermodynamics, in order for heat to transfer kinetically to bulk matter, in order for it to burn your hand, there must be an exchange of entropy. There has to be thermal kinetic drag. The chaos has to spread.
I see where this is going.
Right. But because the vacuum inside the particle is a perfect superfluid ground state with zero entropy, it has no thermal drag. It physically cannot transfer heat to the outside world.
It's too perfect to share its heat. That is wild.
It refuses to interact.
So the vacuum behaves macroscopically as if its temperature is approaching absolute zero, simply because it refuses to interact kinetically. The superhot energy is locked and frozen into supercool structural coherence.
Frozen fire is a fantastic way to conceptualize it. The energy is immense, but it is locked into a state of absolute frictionless order. And there is one more crucial property of this BEC that Banić points out, which ties this whole theory really neatly with observed reality.
Oh, what's that?
The vacuum-Meissner effect.
The Meissner effect. That term usually comes up when talking about superconductivity, right? Like those videos of supercooled magnets levitating in midair over a track.
You're thinking of the exact right phenomenon. A standard superconductor, when you cool it below its critical temperature, actively expels all external magnetic fields from its interior.
Right, the magnetic field lines actually bend around it.
Yes, this is called perfect diamagnetism. Well, Banić proves mathematically that because the interior of a particle is a macroscopic quantum wave function, a BEC, it behaves exactly like a superconductor. It actively expels external magnetic field lines. It drives its relative internal magnetic permeability below 1.
Wait, protons and neutrons are diamagnetic. We already know that from standard experiments, right?
We do, but standard physics often treats that just as an empirical fact, just a measured property that we accept.
Just a quirk of the particle.
Right. But this framework provides the underlying structural reason for it. The diamagnetism of a nucleon isn't just a mathematical quirk. It is the physical, undeniable signature of a Bose-Einstein condensate living inside the particle.
That is just, man, it is an incredible feeling when a theoretical framework doesn't just invent new math, but actually explains a weird quirk of reality that we already knew about. It elegantly solves multiple problems at once.
It really forces a profound shift in perspective. I mean, the mass of your body, the desk, the steering wheel, it's quite literally made of these highly dense, localized thermal bubbles of polarized vacuum fluctuations.
It's kind of beautiful.
They are superheated by their own unimaginable density, yet perfectly shielded and supercooled by their own quantum coherence.
I'm not going to lie, it fundamentally changes how you look at yourself in the mirror.
Sure.
You're not just made of dead matter. You are a walking, breathing collection of trillions of supercooled Big Bang fragments, all holding back unimaginable fire behind a wall of perfect quantum order.
A beautifully stable arrangement of them, thankfully.
Thankfully, yeah. Okay, so that is what is happening at the unimaginably small scale. We have these stable boundaries of trapped energy sitting quietly in our everyday environment.
Right.
But what happens when you take these perfectly balanced little bubbles, these frozen fires, and you throw them into the most violent, high-pressure environment in our solar system? I'm talking about taking this particle physics framework and throwing it into the core of our sun.
And this is where the framework proves its robustness. If we connect this microscopic structure to the bigger macroscopic picture, this theory doesn't just rewrite quantum mechanics, it completely rewrites astrophysics.
Okay, let's get into it.
And it specifically takes aim at one of the great, glaring, unresolved mysteries of standard astrophysics, the coronal heating problem.
Right. Let's set the stage for this anomaly, because for a long time, I had absolutely no idea the sun was doing something it fundamentally shouldn't be doing.
Most people don't.
I think anyone who has looked at a diagram of the sun might assume it works like a giant campfire in space. The core is where the fusion happens, so it's the hottest. Then you move out to the surface, and it gets cooler. And if you move away from the surface into the atmosphere around the sun, it should get even cooler.
That is the perfectly logical assumption based on classical thermodynamics. A heat source radiates outward, and the temperature drops as you move away from the source.
Makes total sense.
And if we measure the visible surface of the sun, the photosphere, that logic holds up perfectly. The surface is indeed around 6,000 Kelvin. It's incredibly hot, but comparatively tame for a star.
Okay.
However, when astronomers measure the temperature of the extended atmosphere, the corona, which is that glowing halo you see during a total solar eclipse, it suddenly spikes to millions of degrees.
Which is completely insane when you really think about it. To use the campfire analogy again, it's like walking away from a roaring fire, stepping out into the freezing woods, and suddenly the air itself, 10 feet away, is 1,000 times hotter than the coals you just left.
It defies everyday logic.
How does standard astrophysics explain that?
Well, standard models rely on two main mechanisms: thermonuclear fusion in the core to generate the heat, and classical magnetohydrodynamics, or MHD, in the outer layers to move it around.
Let me stop you. Magnetohydrodynamics. That's a mouthful. What does it actually mean in this context?
Simply put, it's the study of how magnetic fields interact with electrically conducting fluids like plasma. Standard models try to explain this extreme coronal heat by suggesting that acoustic waves, literal sound waves bouncing up from the turbulent surface, or magnetic field lines snapping and reconnecting, are somehow transporting energy from the surface up into the atmosphere.
But I'm guessing that math doesn't really work out.
It constantly struggles. The acoustic wave theory fails because those waves dissipate far too quickly to account for the millions of degrees in the extended corona. They just don't have the reach.
They fizzle out.
Exactly. And while magnetic reconnection does release energy, standard MHD models struggle to cleanly support the sheer, sustained volume of heat localized strictly in that extended atmosphere. The energy budget always seems to come up short.
Enter postulate 16th from Banić and Vrbovsky, the electrodynamic star.
This postulate shifts the astrophysical paradigm completely. It states that the sun is not just a classical thermonuclear fusion reactor. That is happening, yes, but it is also operating as a macroscopic electrodynamic vacuum resonator.
Okay, let's unpack that term. A macroscopic electrodynamic vacuum resonator. What does that actually mean for our little supercooled bubbles of mass? How do they behave differently inside a star?
Let's think about the environment deep inside the solar core. You have an extreme gravitational potential, and consequently, an extreme vacuum potential. This creates a massive external vacuum polarization pressure that presses inward on every single nucleon.
Let me make sure I'm mapping this back to what we learned in Section 1. The Higgs vacuum pressure we talked about earlier, the water pressure of that infinite ocean that stabilizes the particle, is being artificially amplified.
Exactly.
The walls of the pressure cooker are being squeezed even harder by the sheer gravity and density of the sun's core.
Precisely. Under normal, everyday conditions on Earth, a particle's boundary is in dynamic equilibrium. Its outward electrostatic self-repulsion, the force trying to blow the bubble apart, perfectly balances the inward Higgs vacuum pressure trying to crush it.
Right, they equal out.
But deep in the solar core, that inward vacuum pressure becomes completely overwhelming. It literally overpowers the electrostatic repulsion. It forces the physical boundaries of the protons and electrons to severely compress.
So they actually shrink.
Yes, the boundary radius of a particle in the solar core, which they denote as a subcore, becomes significantly smaller than its standard relaxed rest state radius, sub-zero.
Okay, so the actual physical size of the proton shrinks. But what does this mean for the energy inside it? If you have all that latent energy, all that frozen fire, and you squeeze it into a smaller box, what happens? Does the particle just get smaller and stay the same mass?
No, and this is where the framework's definition of virtual mass comes into play. In this model, virtual mass is inversely proportional to the boundary radius.
Inverse proportion. So as the radius gets smaller, the mass gets bigger.
Exactly. As the boundary shrinks under that immense core pressure, the particle actually becomes physically heavier in terms of its virtual mass. The particle is actively storing immense amounts of electrodynamic field energy within its newly compressed charged shell.
Wait, let me see if I can visualize this. It sounds almost mechanical. Are they acting like coiled springs? By squeezing the proton down, the solar core is packing external potential energy into the very physical boundaries of the particle.
That is a perfect analogy. You are winding up billions of tons of subatomic springs. The plasma in the solar core isn't just hot, it is structurally, physically loaded with stored mass energy.
Okay, but how does winding up springs in the core heat the corona, which is millions of miles away on the outside of the sun?
Through the mechanical churn of solar convection. The interior of the sun is essentially boiling.
Right.
Massive convection updrafts carry this highly compressed, heavily loaded plasma outward from the core, up through the radiative zone, up through the convective zone, toward the surface. Eventually, this plasma is ejected along magnetic flux tubes out into the solar atmosphere, the corona.
I see exactly where this is going. The corona is a low-pressure environment.
Exactly. As that plasma shoots out into the extended atmosphere, it experiences a massive, rapid drop in external vacuum polarization pressure. The crushing weight of the core is suddenly just gone.
And without that inward pressure holding it together, the spring is released.
The intense outward electrostatic self-repulsion of the nucleons immediately takes over. The coiled springs are released. Their physical boundaries are forced to rapidly expand to thermodynamically relax back toward their unperturbed rest state radii.
The compressed radius, a sub-core, violently expands back to a sub-zero.
Yes.
But hold on, if the mass increased when the boundary shrank, what happens to all that stored mass energy when the boundary expands again? It can't just disappear.
You're right, the conservation of energy is absolute. As the boundary expands, the virtual mass decreases. That excess electromagnetic field energy, which mathematically is defined as delta m sub v times c squared, the change in virtual mass times the speed of light squared has to go somewhere.
Where does it go?
It is literally peeled off the boundary and radiated away into the surrounding vacuum.
Whoa. So the particle sheds its own mass energy as radiation.
Yes. And because you have billions of tons of this compressed plasma continuously being ejected into the corona, you have a collective, continuous shedding of subatomic mass energy. This massive decompression saturates the coronal vacuum with intense, extreme ultraviolet EUV and soft X-ray radiation.
That is absolutely brilliant. It flips the whole problem on its head. The corona isn't being heated from below by sound waves flashing up from the surface like a hot plate.
No, it's not.
It is being heated from within. The plasma itself is carrying the fuel up from the core in the form of compressed mass boundaries and then detonating, decompressing once it hits the thin atmosphere.
It elegantly answers the exact question that has plagued standard physics for decades. Why is the heating localized in the extended atmosphere rather than the surface?
Yeah, why there specifically?
Aushilot-Sixik says it's because the thermodynamic relaxation of these boundaries only triggers violently when the plasma reaches a significant low-pressure drop. The surface is still too pressurized. The extended atmosphere is where the spring finally snaps open. The heat of the corona is simply the direct radiative exhaust of subatomic mass decompression.
So if I'm listening to this and trying to picture it, it's like realizing that a car engine isn't being heated by the combustion chamber, but rather the exhaust pipe itself is actively detonating the fuel once it hits the open air.
That's a great way to put it.
The sun breathes. It is literally a macroscopic engine inhaling mass, compressing it with gravity, exhaling it through convection, and shedding the excess energy to heat its own halo.
It's a breathtaking mechanism, and it relies entirely on the fact that the particle boundary is flexible. It's compressible.
Which brings us naturally to the ultimate question of scale.
Mhm.
We've seen how remarkably stable these boundaries are in the desk in front of you. We've seen how they dynamically compress and expand when subjected to the extreme environments inside stars.
Yeah.
But there's a glaring question underlying all of this. What dictates their perfect resting shape in the first place? Why a sub-zero?
That is the million-dollar question.
Right. If the boundary of a particle is just a balance of outward electrostatic pressure and inward Higgs vacuum pressure, what sets the default size of matter? When a particle isn't inside a star, why doesn't it just keep expanding into infinity until it dissolves?
Or a collapse.
Exactly. Why doesn't it collapse entirely under the Higgs pressure into a microscopic black hole? What is the architectural blueprint that says a proton must be exactly this size?
That question leads us directly to the third and final paradigm shift we need to discuss today. It moves us away from astrophysics and into the pure structural geometry of the universe. It involves the most famous, seemingly arbitrary number in all of physics.
The fine structure constant, alpha.
Yes. Alpha, it is roughly equal to 1 over 137.
I feel like every time I read a book about quantum physics, this number shows up like a ghost haunting the math.
Because it is literally everywhere. In standard quantum electrodynamics, the fine structure constant is an axiomatic, dimensionless parameter. It dictates the strength of the electromagnetic interaction between elementary charged particles.
So it controls electromagnetism.
Essentially, yes. It determines how light and matter interact. It is the reason atoms hold together the way they do, which means it's the reason chemistry exists, which means it's the reason life exists.
But in the standard models,
Yeah.
it's just a given.
Exactly. It is just a dial turned to a specific setting, and no one knows why it is that exact value. Richard Feynman, one of the greatest physicists of the 20th century, famously obsessed over this number.
Oh, really?
Yeah, he called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He suggested that all good theoretical physicists put this number up on their wall and worry about it.
Just a number handed down from the cosmos.
Yeah.
The universe's serial number. But based on everything we've talked about today, I'm guessing Banić and Vrbovsky do not accept magic numbers in their framework.
Not at all. In their specific paper, titled The Hydrodynamic Origin of the Fine Structure Constant, they resolve its ontological nature once and for all through postulate 8. And to do this, they lean heavily on a concept we all learned in basic physics: wave-particle duality.
Okay, let's unpack this. How does wave-particle duality, the idea that light and matter can act like both a particle and a wave, explain a magic number?
Well, in the Redefined Mass framework, we have established that particles are not dimensionless points, which is a major departure from standard QFT. They have finite, three-dimensional, spherical, subquantum boundaries. But they possess an inseparable dual structure.
Explain that dual structure.
So there is the localized geometric boundary itself, the dense bubble of trapped energy. We can call this the particle state.
Okay, the bubble's the particle.
Right. But because this bubble exists within a superfluid vacuum, its very existence and rotation create an extended circulating quantum phase slip in the fluid around it. We can call this surrounding disturbance the wave state.
Ah, okay. Let me try an analogy. It's like throwing a spinning top into a calm pool of water. You have the hard physical top spinning in the center in the particle, and then you have the constant ripples and currents it creates in the water extending outward the wave. You can't have the top spinning in the water without creating the ripple. They're two halves of the same physical event.
That is a brilliant way to visualize it. And Banić realized something profound. The fine structure constant isn't a magical tuning dial. It is derived simply by taking the ratio of the physical energy of these two states, the particle and the wave.
Let's do the math on this.
Yeah.
I know we promised no heavy jargon, and we've avoided equations for the most part, but I want to see how this derivation works step by step, because it sounds like the payoff of the entire framework.
It is incredibly elegant, and I think we can make it very accessible. Let's look at the numerator first, the particle energy. This is the energy required to assemble the physical localized boundary of the particle. The energy required to blow the bubble in the first place against the vacuum pressure.
Okay, the energy of the bubble itself.
Mathematically, this is calculated as its electrostatic self-energy. If we write it out, it is W subparticle equals E squared divided by 8 pi epsilon 0, a sub-zero.
Let's translate that out of math.
Basically, it's the charge of the particle, which is E squared, divided by some geometric constants, and crucially divided by a sub-zero, which is the radius of the boundary. Notice that the boundary radius, a sub-zero, is sitting right there in the denominator of this term.
Okay, got it. The energy it takes to build the bubble depends inversely on the size of the bubble. That's the top half of our ratio. What of the bottom half, the denominator, the wave energy?
The characteristic energy associated with the extended wave, the ripple in the superfluid vacuum oscillating across the diameter of this boundary, is given by the standard hydrodynamic quantum energy scale.
And how do we write that?
We write it as E subwave equals h bar c divided by 2, a sub-zero. H bar is Planck's constant, c is the speed of light. And once again, look at what is sitting in the denominator of this term.
The boundary radius, a sub-zero. Wait a second, I'm trying to picture the algebra here. If a sub-zero is in the denominator of the top equation for the particle, and a sub-zero is also in the denominator of the bottom equation for the wave, if you divide a fraction by a fraction.
When you divide the localized electrostatic boundary energy by the hydrodynamic vacuum circulation energy, the boundary radius, a sub-zero, algebraically cancels out perfectly.
It just vanishes from the equation.
Completely. The physical size of the particle is eliminated from the math. The result of dividing those two terms leaves you exactly with E squared over 4 pi epsilon 0 h bar c.
Which is, let me guess.
Which is the exact standard physics definition of alpha, the fine structure constant.
My mind is officially blown. So
Yeah.
by taking the ratio of the localized particle boundary to the hydrodynamic wave energy it creates in the vacuum, the actual physical dimension of the particle cancels out, leaving only this pure dimensionless constant. That means scale doesn't matter. The ratio is intrinsic to the geometry of the vacuum itself.
It is a spectacular mathematical and physical identity. Alpha is exactly the ratio of the localized electrostatic self-energy of the particle boundary to the hydrodynamic wave energy of the surrounding superfluid vacuum.
It's like finding the golden ratio of reality. It's built into the architecture. But what does it actually represent physically? If it's a ratio balancing these two things, what is it actually doing in the universe?
Banić defines it as the universal thermodynamic efficiency limit of the Ginzburg-Landau vacuum phase transition.
Okay, I am going to need an ELI 5 on Ginzburg-Landau vacuum phase transition.
Sure. Think about what happens when a high-energy particle collision occurs, like in the Large Hadron Collider. You smash two protons together, they shatter, and their energy is dumped into the vacuum.
Total chaos.
Right. The vacuum immediately attempts to localize that scattered field energy back into stable spherical charge boundaries. It tries to renucleate new particles out of the chaos. This process of energy coalescing back into a stable form is a phase transition, mathematically described by Ginzburg-Landau theory.
So it's the vacuum trying to heal itself by making new particles.
Exactly. But the surrounding superfluid vacuum is highly dynamic, it's fluctuating, it's vibrating. Alpha dictates the absolute maximum efficiency at which the vacuum can localize electromagnetic field energy into a stable 3D bubble without the surrounding wave energy tearing it apart.
I think I see it. It's an efficiency limit. The universe can only pack energy into a particle with about a 1 in 137 efficiency relative to the chaotic wave action of the fluid around it.
Right.
If the universe tried to be more efficient, if it tried to pack more energy into that space, the outward wave energy would overpower the boundary and it wouldn't hold. It would undergo immediate relativistic string collapse.
You've got it. It represents the critical equilibrium threshold. It is the fundamental geometric scale factor that bridges the particle's localized charge boundary. Its classical radius with its extended superfluid phase boundary, its Compton wavelength. Alpha is not an arbitrary dial turned by a cosmic creator for no reason.
It's structural.
It is the inevitable structural hydrodynamic balancing act of wave-particle duality. It is the only mathematical ratio where matter can exist without instantly destroying itself.
That is just profound. It takes something that has been treated as a mathematical placeholder, a ghost, for nearly a century and turns it into a physical, structural necessity for the existence of matter.
And if we look back at the whole of this deep dive, that is the overarching theme of Banić and Vrbovsky's work. They do not accept magic. They take standard mathematical abstractions and demand physical mechanisms for them.
I want to take a moment to recap this incredible arc we've been on today, because we have covered a massive amount of conceptual ground. We started at the absolute smallest scale, looking at a single proton in a desk.
The frozen fire.
Yes. We realized that its mass isn't just dead weight. It's a localized, supercooled Bose-Einstein condensate. It is a perfectly frozen phase transition, hiding 39.5 GeV of latent energy over 400 trillion degrees locked away, with exactly zero thermodynamic entropy, which is why it doesn't incinerate us.
The entropy paradox, perfectly resolved by the vacuum Meissner effect and the mechanics of quantum superfluidity.
Then we zoomed out from the desk to the sun. We saw how those very same subatomic boundaries, when subjected to the crushing vacuum pressure of the solar core, act like coiled springs, storing mass energy.
The compression of the boundary radius.
Convection physically carries them to the surface, and as they hit the low-pressure drop of the corona, they decompress. They violently shed their excess virtual mass energy, bathing the solar atmosphere in extreme ultraviolet light and X-rays.
Postulate 6.6, the electrodynamic star, proving that astrophysics and quantum vacuum dynamics are inextricably linked, solving coronal heating from within the plasma itself, rather than relying on failing models of acoustic waves from below.
And finally, we asked what keeps those tiny explosive boundaries structurally stable in the first place, which led us to alpha.
The magic number.
But it isn't magic. It's the exact scale-independent ratio of a particle's electrostatic self-energy to the hydrodynamic circulation of the superfluid vacuum around it. It is the ultimate efficiency limit of reality.
It is a breathtakingly unified vision of physics. One elegant structural truth. The compressible dual-state nature of the subquantum boundary cascading up through the scales of reality to explain everything from a magnet on your fridge to the heat of the solar corona to the fundamental constants of the universe.
It really is. It completely changes how you see everything. And it leaves me with one final provocative thought for you listening. We started this deep dive by asking you to touch your desk. We look around our room, we touch our physical objects, and we think of them as solid.
But they aren't.
No, we now know, through this framework, that solid matter is actually just a localized, supercooled phase transition of a violently energetic vacuum. We look up at our stars, and we now know they are macroscopic engines, constantly manipulating, compressing, and relaxing those subatomic boundaries to generate light and heat. So what does that mean for the vast, seemingly empty voids of space between the stars?
The vacuum itself.
Exactly. If the empty vacuum is the underlying superfluid canvas that makes all of this possible, if it contains that massive background Higgs pressure, what happens if you were to truly agitate that empty space? What else is just sitting there in the dark, perfectly balanced, completely invisible, just waiting to be decompressed?
That, I believe, is the next great frontier of physics.
Thank you so much for taking the plunge into this deep dive with us today. It's been a mind-bending journey through the Redefined Mass framework. Keep questioning the reality around you, and the next time you rest your hand on your desk, remember the frozen fire inside it. Until next time.